In this section, we'll be talking about the important topic of acid-base chemistry. Now, in order to understand acids and bases, we have to know their definitions first of all. An acid is a compound that, when placed in water, dissociates to yield a hydrogen ion and a conjugate base. For example, what we show here is acetic acid. It has a carboxylic acid group, the COOH, and when it's placed in water, the hydrogen comes off as a proton and leaves a negatively charged acetate molecule behind. The acetate is the conjugate base. Now, a base is a compound that combines with protons in water to form a conjugate acid. So, for example, we have ammonia, this NH3, that can combine with an extra proton to form ammonium ion, which is NH4+. Now, the general expression, or the equation that we write to describe acid dissociation is as follows. We have an acid, which is represented by HA, and that is converted to a proton plus the conjugate base, which we designate A-. Now, this occurs at a particular rate. There is a forward rate constant, K1, which describes the rate at which the acid dissociates into the proton and conjugate base. And there's also these reactions are all reversible too, and there's a K1 term which indicates the rate at which this converts back to the acid, that the conjugate base and the proton combine to form the acid. The rate of the reaction is determined by the concentration of the substrate times the concentration of that rate constant. So the concentration of the acid, HA, times the rate constant will give us the rate at which this reaction goes. But more importantly than that, this gives us an idea of how easily this base dissociates. If K1 is much greater than K-1, that means that this acid tends to dissociate very easily and produces a lot of protons when placed in water. On the other hand, if the K-1 is higher than K1, then this means that this is an acid which doesn't dissociate very well and produces very few protons when placed in water. Now, eventually what will happen is that these two rates will reach an equilibrium, and that allows us to define a dissociation constant. So at particular concentrations, then, the rate of K1 and the rate of K-1 will be equal, and that defines this association or dissociation constant Ka. So K1 over K-1 then can be described as Ka, and that is then the concentration of the proton plus the concentration of the conjugate base, and divide that by the concentration of the acid, and that'll give you the dissociation constant Ka. Now we take the negative log of Ka to give us a value that we call pKa. And pKa is an expression of the strength of an acid, or how likely it is to dissociate. Now I described that a little bit already. You can imagine if K1 is much greater than K-1, then the Ka is going to be relatively high, and so you will get a low pKa in that particular situation. So acids that have a low pKa, say less than 2, dissociate readily. That means K1 is much greater than K-1, and so these are strong acids. These are things like sulfuric acid and hydrochloric acid that give up their protons extremely readily. Now, acids in which the K1 is greater than the K-1 is greater than K1, then they have a higher pKa in it. You can do the math to figure that out. A higher pKa, say greater than 10, these are things like citric acid or acetic acid, and these are weak acids because they bind the proton more tightly, and when they're placed in water, they dissociate much less readily and produce fewer protons. Now, pH, then, is a measure of the acidity of a solution, and we'll relate that to pK in just a minute. The pH is defined as the negative log of the proton concentration in any given solution. A neutral solution has a proton concentration of 10 to the -7th molar, which translates into a pH of 7. An acidic solution has a higher concentration of protons, which means that the concentration is greater than 10 to the -7th, and so the pH is going to be less than 7. A basic solution has a lower concentrations of protons, less than 10 to the -7th molar, and thus will have a pH of greater than 7. Now, pH can be related to the pKa of a given acid using what we call the Henderson-Hasselbalch equation. And that equation is as follows. pH is equal to pKa plus the log of the concentration of the conjugate base divided by the concentration of the undissociated acid. Now this is one of those equations, one of the few equations that you really need to memorize for the USMLE. Now, one more definition that we need to discuss, and that's the definition of a buffer. Now this is really important in physiologic systems because buffers allow our bodies to stay at a constant pH, and we'll discuss that more in a few minutes. But a buffer is defined as a solution of a weak acid and its conjugate base that has a tendency to resist changes in proton concentration. Now, maximum buffering occurs when the concentration of the acid is approximately equal to the concentration of its conjugate base. So remember the Henderson-Hasselbalch equation. So if HA is approximately equal to A minus, or the conjugate base, then the log of that is going to be 0, right? The log of 1 over 1, say, for example. And so pH will be roughly equal to pKa in that case. So this generates what we call a buffer titration curve. On the y-axis, we show increasing pH. On the x-axis, we show increasing base. Now, a buffer is a substance that causes the sigmoid curve that you see here to be flattened in a particular zone. That means for a certain range of pH, you can increase the base a lot without changing the pH very much in that particular buffer zone. Now, every buffer has a different pH range, a different buffer zone that it's functional at. So depending on the pH at which you want to maintain a solution, you will use a different buffer. In human plasma and extracellular fluid, the primary buffer is the carbon dioxide, carbonic acid, bicarbonate system. And that's expressed in the following equation. On the left-hand side, you have a proton, which combines with a bicarbonate molecule, that's the conjugate base, to form a molecule of carbonic acid. And that's the acid. And that's the buffer. So the transition between bicarbonate and carbonic acid is what provides the buffering capacity of extracellular fluid. Now, that carbonic acid then is rapidly converted to carbon dioxide and water by carbonic anhydrase. And so this enzyme carbonic anhydrase is responsible for both of these transitions. Now, in this system, the CO2, because it's rapidly converted from carbonic acid by the carbonic anhydrase, the CO2 behaves like the acid. And so we can put that, the partial pressure of CO2, in the denominator of the Henderson-Hasselbalch equation with a conversion factor. The conjugate base is bicarbonate, and so we put the concentration of bicarbonate in the numerator of the Henderson-Hasselbalch equation. So the Henderson-Hasselbalch equation for this is pH equals 6.1, which is the pKa for this system, plus the log of the concentration of bicarbonate over this conversion factor times the partial pressure of CO2. Now, I don't want you to memorize this particular equation. I doubt that you'll be able to calculate pH on the test based on bicarbonate concentration and the partial pressure of CO2. But what I do want you to remember is then the relationship between bicarbonate concentration and pH, and the relationship between the partial pressure of carbon dioxide and pH. Because this helps us understand how the body can regulate pH by altering the bicarbonate concentration and the partial pressure of CO2. For example, we can decrease pH by decreasing the bicarbonate concentration, or we can decrease pH by increasing the partial pressure of CO2. We can increase pH by increasing the bicarbonate concentration, or by decreasing the partial pressure of CO2. Now, this system is ideal since the concentration of bicarbonate and the partial pressure of CO2 are easily regulated by the body. Now, the concentration of bicarb can be regulated by increased or decreased excretion of bicarbonate from the kidneys. The normal range is approximately 22 to 26 millimolar. The partial pressure of CO2 is regulated by increasing or decreasing ventilation at the lungs. When we increase ventilation, the partial pressure of CO2 goes down. When we decrease ventilation, the partial pressure of CO2 goes up. The normal range for PCO2 is approximately 38 to 42 millimeters of mercury. And the combination of these two factors maintains our body pH of all our cells in our extracellular fluid between approximately 7.35 and 7.45. And this is important because all of our enzymes and physiologic processes work optimally in that pH range. Now, there are disorders which occur when the pH falls beneath that range or rises above that range. Acidosis occurs when the pH drops below 7.35. And there are two general causes of this. One is hypoventilation. When we hypoventilate, when we don't exchange carbon dioxide very well in the lungs, the carbon dioxide builds up. And remember, that's in the denominator of the Henderson-Hasselbalch equation. So when CO2 increases, the pH goes down, and this leads to an acidosis. This is called respiratory acidosis because it's acidosis that has a primary respiratory cause. Now, if we have a respiratory acidosis, our kidneys can respond to that and adjust the pH by retaining bicarbonate at the kidneys. Now, remember, the bicarbonate is in the numerator of the Henderson-Hasselbalch equation, so by increasing the concentration of bicarbonate, we're able to increase the pH back to the normal level. Now, the other thing that can cause acidosis is addition of acid by any number of causes. What happens when we add acid, this titrates out the bicarbonate, that gets converted to CO2 and water, and that decreases the bicarbonate concentration in the fluid. As the bicarbonate concentration goes down, so goes down the pH. Now, we can adjust to that, or we can compensate for that by hyperventilating, decreasing the partial pressure of CO2, which leads to an increase of pH back to the normal level. Alkalosis, on the other hand, occurs when the pH rises above 7.45. And there are two general causes, which are exactly similar to the causes of acidosis. When we hyperventilate, this causes decreased partial pressure of CO2. When we decrease the partial pressure of CO2, the pH increases, according to the Henderson-Hasselbalch equation. So we get an alkalosis that's caused by a primary respiratory disorder, and so we call that respiratory alkalosis. The kidneys, again, respond to this by increasing the excretion of bicarbonate. As the bicarbonate concentration goes down, the pH goes down back to the normal level. We can also get alkalosis by the loss of an acid or by the addition of a base, and this is called metabolic alkalosis. Anything that increases the bicarbonate concentration. So when the bicarbonate concentration goes up, according to the Henderson-Hasselbalch equation, the pH has to go up as well. The body responds to this by hypoventilating, by retaining CO2 and increasing the partial pressure of CO2, which decreases the pH back to its normal level. Now, this is a handy chart which is really useful in helping you remember the changes that occur in these four different types of alkalosis and acidosis, acid-base disorders. In respiratory alkalosis and metabolic alkalosis, the pH is going up. In respiratory acidosis and metabolic acidosis, by definition, the pH is going down. In respiratory alkalosis, the pH rises because there's a decreased partial pressure of CO2. The kidneys, and that increases the pH. The kidneys respond to this by decreasing the concentration of bicarbonate and trying to bring the pH back to the normal level. So in respiratory alkalosis, the pH will be high, the bicarb concentration will be low, and the PCO2 will be low. In respiratory acidosis, the pH is decreasing because we have an increased partial pressure of CO2. The kidneys respond to that by retaining bicarb, increasing its concentration in an attempt to bring the pH up to the normal level again. So in respiratory acidosis, pH will be low, bicarbonate concentration will be high, and PCO2 will be high. In metabolic alkalosis, the pH is high because there is a retention of bicarbonate. The bicarbonate concentrations are high, and so this drives up the pH. The lungs respond to that by hypoventilating, retaining CO2, and increasing PCO2. So in metabolic alkalosis, the pH is high, the bicarb concentration is high, and the PCO2 is high. In metabolic acidosis, the pH obviously is low by definition, and it's low because the bicarb concentration is low. The lungs respond to that by hyperventilating, by blowing off CO2, decreasing the PCO2, and bringing bring the pH back down to the normal level. So in metabolic acidosis, the pH is low, the bicarb is low, and the PCO2 is low. Some of these acid-base disorders can be illustrated by the following clinical vignettes. A 22-year-old man with a history of severe depression was found unresponsive by his mother. She found an empty aspirin bottle next to him, indicating that perhaps he had attempted to commit suicide by an overdose of aspirin. Upon physical exam, the patient is stuporous, he's difficult to arouse, he's breathing very fast, a condition we call hyperpnea. His respiratory rate is 36, and he has profuse sweating. An arterial blood gas shows that the pH is low, 7.23. The PCO2 is low, at 26 millimeters per mercury, and the bicarbonate concentration is low at 12 millimolar. The electrolytes are normal, except for the bicarbonate is low, and there's an elevated anion gap of 21. What is this patient's acid-base disorder? He has metabolic acidosis from salicylate poisoning. Now, this patient has a metabolic acid because an acid, in this case salicylic acid or aspirin, has been added to the system. Now, again, this titrates off the bicarbonate, which is converted to CO2 and blown off, and that means that the bicarbonate concentrations in the serum are going to be low. The most reliable clinical sign of metabolic acidosis is hyperventilation. Remember that the body is going to force itself to breathe really fast to decrease the partial pressure of CO2, and this drives the pH back up and tries to compensate for the metabolic acidosis. Now, other specific signs of salicylate poisoning are things like sweating, agitation or confusion, and lethargy. Conscious patients may also notice tinnitus or a ringing of the ears and constipation. The treatment of acute severe salicylate intoxication includes things like activated charcoal, giving plenty of fluids, and correcting the electrolyte and acid-base disturbances which we've described. You can correct the acidosis by giving sodium bicarbonate, which brings the bicarbonate concentration back up. A different acid-base disorder can be described in the following clinical vignette. A 5-year-old girl presents to the emergency room because she's been vomiting for a long time, about a day. A day prior to this, she ate some ice cream from a street vendor and got food poisoning, and that caused her to vomit. Physical exam shows that she has tachycardia, she has sunken eyes, she has dry mucous membranes, and she has poor skin turgor. These are all indications of dehydration. An arterial blood gas in this particular individual shows an elevated pH, a pH of 7.51. Partial pressure of oxygen is increased at 50 millimeters of mercury, and the bicarbonate concentration is increased at 30 millimolar. Other significant labs show hyponatremia and hypochloremia with an elevated BUN, and these are all, again, signs of dehydration. What is this patient's acid-base disorder? This is an example of metabolic alkalosis, which occurs from protracted vomiting. Protracted vomiting causes a metabolic alkalosis because of the loss of stomach acid in the vomitus. This alkalosis is compounded by dehydration, which can cause increased bicarbonate resorption in the kidneys. So you get an increased bicarbonate concentration because you lose acid, and also because you retain bicarb in the kidneys. This is called a contraction alkalosis. Now, the PCO2 is elevated because of the compensatory response to the alkalosis, which is hypoventilation. And you treat this with IV fluids and antiemetics to prevent her vomiting. This concludes the section on acid-base.